Tonight, as you settle in and close your eyes, we are going to travel very, very far from home. We are going to drift beyond the clouds and the moon, past the planets, past the quiet dust between the stars, into the deep, dark ocean of space. And there, in that silent darkness, we will meet one of the strangest and most mysterious objects in the universe. A black hole. Imagine you are floating in space. There is no up and there is no down. Around you, stars glimmer like tiny pinpricks in an endless black curtain. Some shine white and blue, sharp and bright. Others glow softly in red and orange, like distant embers. Now, far away, you notice a patch of the sky where something seems missing. No twinkling stars, no glowing clouds of gas, just a round, perfectly dark spot. At first, you might think it's simply empty, just a blank part of the sky. But the longer you look, the stranger it becomes. Near the edge of this dark circle, the stars look a little distorted, as if their light is bending, curving, almost sliding around something invisible. You're looking at the shadow of a black hole. A black hole is not like a planet or a star or a rock. It isn't an object you can land on. It isn't something with a surface that you could touch. A black hole is a place in space where gravity has become so strong, so incredibly powerful, that nothing can escape it. Not a spaceship, not a planet, not even light. Imagine throwing a ball up into the air on Earth. It goes up, slows down, then falls back down. If you could throw it hard enough, so hard that it never fell back, you would have reached Earth's escape speed. For Earth, that escape speed is about 11 kilometers per second. That's incredibly fast, but still possible for rockets. Now imagine a place where the escape speed isn't just faster than any rocket, or faster than anything we could build, but faster than light itself. Light is the fastest thing we know of in the universe. And at a black hole, even light cannot get away. It is a hole in the sense that, once you cross its boundary, there is no way out. To understand how black holes are born, we need to visit a star. Not our sun, but a star much bigger. A star many times more massive. Picture a bright, blue-white star, heavy and hot, burning with a fierce light. Inside that star, deep in its core, something very important is happening. Gravity is pulling everything inward, squeezing the star's gas toward the center. But the star is not collapsing, because something pushes back. The star shines because of nuclear fusion. Tiny atomic nuclei in its core crash together and fuse, releasing enormous amounts of energy. That energy pushes outward, like pressure inside a balloon, balancing the inward pull of gravity. For millions and millions of years, gravity and pressure stay in balance. The star lives a long, bright life. But nothing in the universe lasts forever. Eventually, the star begins to run out of fuel in its core. The fusion slows, then begins to fail. The outward pressure weakens. Gravity does not. With less pressure pushing back, gravity starts to win. The star's core begins to shrink. The outer layers begin to fall inward. And then something dramatic happens. The heavy star collapses, its core crushed in a fraction of a second. The outer layers slam down onto the core, bounce, and explode outward in a vast, brilliant blast called a supernova. For a moment, that dying star can shine brighter than an entire galaxy. What happens to the core that remains? If the original star was large enough, with enough mass, gravity keeps pulling on the collapsed core, harder and harder, until there is nothing that can stop it. Not the pressure between atoms, not the pressure inside atomic nuclei. The core shrinks past any normal form of matter we understand. It collapses into something so dense, so small, and so heavy that it becomes a black hole. You might wonder, what is inside a black hole? The honest answer is that we do not fully know. Our best theories of gravity say that at the very center of a black hole, the collapsing matter is crushed into a point of infinite density called a singularity. But infinite density is another way of saying that our current understanding breaks down there. We do not yet have a single final theory that combines gravity and quantum physics, the physics of the very small, in a way that can clearly describe what happens at the center. So scientists use careful language. We say, according to our current theory of gravity, if you follow it all the way in, it predicts something we call a singularity. We also know that this is a sign that our theory is incomplete. In simpler words, we know enough to know that we don't know everything. Even if we do not know exactly what lies at the center, we understand the region around a black hole very well. A black hole has a boundary called the event horizon. Imagine an invisible sphere around the black hole. If you are outside this sphere, you can escape. If you move fast enough and in the right direction, if you cross this invisible surface, you cannot escape, no matter what you do. No signal can get out from inside the event horizon. no object, no light. The event horizon is like a one-way door. You can go in, but you can never come back out. This does not mean that you would feel anything special as you pass it. There is no wall, no bright ring, no physical barrier. You would simply drift across an invisible boundary, and from that point on, every possible path you could take would lead you deeper inward. You could not turn around. You could not send a message out. For you, everything would feel normal for a little while. But for the outside universe, you would be gone. Let's slow down. Let's imagine peacefully what it's like to be near a black hole, but at a safe distance. You are in a ship, floating near a medium-sized black hole, perhaps one formed from a collapsing star. Outside your window, you see a ring of bright, glowing gas swirling around the black hole. This ring is called an accretion disk. It is made of gas, dust, and sometimes even pieces of stars, all spiraling inward toward the black hole. As the material circles and falls, it heats up, growing hotter than the surface of almost any star. It shines in high-energy light, such as X-rays, but to you, safely far away, it is simply a distant, glowing halo. The black hole itself looks like a dark circle at the center, where nothing is visible. Around it, the light from the background stars appears warped and curved, as the intense gravity bends the paths of light beams passing near the black hole. This bending of light is called gravitational lensing. The black hole becomes like a strange funhouse mirror, distorting the image of the universe behind it. If you drifted closer, in your mind's eye, you could watch time itself slow down. Not for you. Your heartbeat, your thoughts, your breathing would seem the same. But if someone far away watched you, they would see you moving slower and slower. Your clock would seem to tick more gently. As you hovered close to the event horizon, from their point of view, your movements would almost freeze. You would appear to be stuck in time, dimming and fading, stopping just at the very edge of the black hole, never quite crossing over. From your own viewpoint, though, nothing so special would happen. You would cross the horizon and fall inward. Why the difference? The answer is that gravity affects time. The stronger the gravity, the slower time passes, compared to regions with weaker gravity. Near the black hole, gravity is extremely strong, so local time runs differently than far away. We call this effect gravitational time dilation. This idea that gravity curves space and slows time comes from a theory called general relativity. It was proposed by Albert Einstein over a century ago. Before Einstein, gravity was seen as a force that acted at a distance, like an invisible pulling. Einstein suggested something deeper. He said, "Mass and energy bend the fabric of space and time." You can imagine space-time as a kind of flexible sheet, like a stretched rubber blanket. If you place a heavy ball in the center, the blanket curves downward around it. If you roll a smaller ball near it, the smaller ball moves along the curved surface, spiraling inward. In a similar way, planets move around stars, and stars move around the centers of galaxies, because space-time itself is curved around heavy objects. A black hole is like pushing that heavy ball deeper and deeper into the blanket until it creates a bottomless well. The fabric of space-time is so deeply curved that all paths lead inward. Once you cross the event horizon, every direction you can travel, even the direction you would call outward, is still a path that leads you closer to the center. In that sense, the black hole is not just an object in space. It is a region of space where geometry itself is twisted to an extreme. You might be wondering, if no light can escape from a black hole, how can we ever see one? How can we know they exist? For a long time, black holes were a mathematical idea, a strange but logical consequence of Einstein's equations. Some scientists thought they might be purely theoretical, never to be seen in reality. But the universe had other plans. We have several ways of detecting black holes, even if we cannot see them directly. One way is to watch how they affect nearby objects. Imagine a visible star orbiting around, something you cannot see. By carefully measuring its motion, its speed, and its path, you can work out how strong the gravity of its unseen partner must be. In some cases, the invisible object is too massive and too compact to be anything but a black hole. We have found many black holes this way by watching stars dance around them. Another method is by observing the bright disks of gas around them. When gas falls into a black hole, it does not usually fall straight in. It swirls in, forming the hot, glowing accretion disk. These disks can be some of the brightest objects in the universe, especially around the largest black holes that sit in the centers of galaxies. Some of these giant black holes power what we call quasars, which can shine so intensely that they outshine all the stars in their host galaxy combined. And then there is another, even more direct way. We can listen to the universe, not just with light, but with ripples in space-time itself. In 2015, a group of scientists using an observatory called LIGO, the Laser Interferometer Gravitational Wave Observatory, detected something that humans had never directly heard before. They detected gravitational waves, tiny ripples in the fabric of space-time, created when massive objects move in violent ways. In this case, two black holes far across the universe had been orbiting each other, spiraling closer and closer until they finally crashed together. The collision released a burst of energy so large that, for a brief instant, it radiated more power than all the stars in the observable universe combined. Most of that energy went into gravitational waves that spread out across the cosmos, gently changing the distances between objects as they passed. By the time they reached Earth, the waves were unimaginably faint, stretching and squeezing distances by far less than the width of a proton. And yet, with careful design and extreme precision, LIGO was able to measure those tiny changes. From this chirp, scientists could tell the masses of the black holes, their distance from us, and details about their final merger. This was like hearing two invisible objects call out to us from across the universe. We are here. We exist. We are black holes. If our sun were somehow squeezed into a black hole, its event horizon would be about 3 kilometers in radius. At the other extreme, we have supermassive black holes. These monsters live in the centers of most galaxies, including our own Milky Way. Our galaxy's central black hole is called Sagittarius A star, or SCA for short. It has a mass about 4 million times that of the Sun. Yet, even with such a huge mass, its event horizon would fit well inside the orbit of Mercury. Some galaxies contain black holes billions of times the mass of the Sun. Between these extremes, there may be intermediate mass black holes, hundreds or thousands of times heavier than the Sun, though these are harder to find and still actively studied. We don't yet fully understand how the largest black holes grow so big in physical processes, at least in principle. If you know everything about a system at one time, the laws of physics allow you to predict its future and, in theory, reconstruct its past. But black holes seem to break this pattern. Anything they consume cannot send information back out, at least not in a straightforward way. This led to a famous puzzle called the black hole information paradox. The story becomes even more complicated when we add another idea: Hawking radiation. In the 1970s, the physicist Stephen Hawking studied black holes using quantum theory. He found that, due to quantum effects near the event horizon, black holes are not completely black. They very slowly emit a faint glow of particles called Hawking radiation. This radiation is extremely weak for large black holes. A black hole with the mass of our Sun would take much than the age of the universe to evaporate in this way. As of now, there is no single answer that everyone agrees on. The paradox has inspired some of the most creative thinking in theoretical physics, and it continues to guide research toward a better understanding of quantum gravity. For all their strangeness, black holes are part of the natural life cycle of stars and galaxies. They are not cosmic vacuum cleaners that roam around, sucking everything in. If our Sun were suddenly replaced by a black hole of the same mass, the Earth would continue to orbit almost exactly as it does now. The main difference would be that there would be no sunlight. Instead of being pulled in, we would simply move around the black hole, just as we now move around the Sun. To fall into a black hole, you still have to get close enough, just as you would have to head straight toward a planet to crash into it. Black holes influence the regions near them, but they do not reach out across the galaxy and steal stars from far away. Around supermassive black holes at galaxy centers, stars and gas can form complex patterns. Some of the material falling in gets heated and blasted outward in powerful jets, beams of particles and energy that shoot out along the black hole's spin axis. These jets can stretch far beyond the galaxy itself, like cosmic searchlights. Paradoxically, black holes, these dark, trapping regions, can be responsible for some of the brightest, most energetic phenomena we observe. They help shape galaxies, regulate how stars form, and may have played an important role in the early growth of structures in the universe. Time runs differently, where paths of light warp inward, and where the laws of physics are pushed to their limits. You think about the star that once lived here. Perhaps it was bright and massive, shining in blue light, giving off warmth to any planets that might have circled it. It was born from a cloud of gas, lived its life, then ended in a violent supernova, leaving behind this dark remnant. The matter that made up that star is not gone. It has simply changed form, transformed into an extreme state. Its mass still curves space-time. Its gravity still shapes the motion of anything that comes near. In a sense, the black hole is part of the star's memory, written into the fabric of the universe. As you continue to circle, you remember that black holes are not rare, exotic things only found in distant galaxies. There are likely millions of black holes just in our own Milky Way. Most of them are quiet, with little or no gas falling in, invisible against the background of space. They are simply there, dark companions to stars, or drifting alone. We have found some of them by watching how they pull on other stars. We suspect many more are waiting to be discovered. And, at the center of our own galaxy, 26,000 light years away, sits Sagittarius A star, our local supermassive black hole. When we look at the center of the Milky Way in infrared light, we can see stars whipping around an invisible point, moving so fast that only a black hole can explain their paths. Each of these tools adds another piece to the puzzle, and at the same time raises new questions. How exactly do supermassive black holes form so quickly in the early universe? What happens to information at the event horizon? What does the interior of a black hole really look like when described by a full theory of quantum gravity? Could tiny black holes, much smaller than stars, have formed in the early universe? And if so, do any still exist? We do not yet know the answers, but the search continues. Black holes, once theoretical curiosities, have become central players in some of the biggest questions science is asking. Yet, for all their complexity, there is something surprisingly peaceful about them when we imagine them from far away. They do not roar or rumble in the vacuum of space. They do not shine or flash by themselves. They sit silently, bending the paths of light, shaping the orbits of stars, and marking the places where the universe has gone to an extreme. In your mind, you drift further back now, pulling away from the black hole's orbit. The glowing ring of gas grows smaller. The black circle in the center shrinks to a dot. Soon, it is only one point among many, lost in the starry tapestry. You keep moving outward. You see the galaxy that surrounds it, a spiral of hundreds of billions of stars, lanes of dark dust, glowing clouds where new stars are born. At its center, the supermassive black hole, invisible now from this distance, holds countless stars in motion, its gravity helping to bind the galaxy together. You move even farther out, seeing other galaxies, each with its own history, its own stars, its own central black hole. Across the cosmos, black holes are scattered like dark seeds in the garden of the universe. Some are tiny compared to their galactic cousins, only a few times the sun's mass. Some are giants, billions of times heavier, powering quasars that shine across billions of light years. They are all connected by the same laws, the same geometry, the same strange interplay of gravity and time. As you drift among these ideas, you might notice a feeling of scale. Our daily worries and routines take place on a world that orbits a modest star in the outer part of a spiral galaxy, in a universe wider than we can truly imagine. Black holes are reminders of how rich and varied that universe is. They show us that reality, when pushed to extremes, can behave in ways that are not intuitive, but are still ordered, lawful, and deeply beautiful. Time slowing near strong gravity, light bending along curved space, stars dying in explosions that briefly outshine galaxies, ripples traveling through space-time like gentle waves on a cosmic ocean. These are not just poetic images, but real phenomena, described by equations and confirmed by instruments. And yet, when we close our eyes, we can also experience them as stories, as quiet journeys into the unknown. If you listen carefully in your imagination, you might almost hear a faint echo of the universe's slow heartbeat, the soft chirp of distant black holes merging, the quiet hum of the cosmic background radiation, the leftover glow from the Big Bang, the steady whirling of galaxies, the silent fall of gas into black holes, turning gravitational energy into light and heat. Everything connected, everything moving, changing, transforming. Black holes are not places of pure destruction. They are part of this cycle. They are places where matter and energy are rearranged, where the known laws are stretched to their limits, making way for new understanding. Galaxies drift for eons. Even the evaporation of a black hole by Hawking radiation would take far, far longer than the age of the universe. We are like brief flashes of awareness inside this ancient, patient cosmos. And in the short time we have already learned to describe objects that bend time, to hear the merging of black holes across billions of light years, and to take images of their shadows. There is something quietly reassuring in that. We may be small, but our curiosity is not. As your thoughts slow, imagine yourself back under a night sky on Earth. You might be lying on your back on a quiet, dark hill. Above you, the Milky Way stretches like a pale river of stars. You know that somewhere in that glow, at the very center, orbits Sagittarius A star, a black hole 4 million times more massive than the Sun. You cannot see it. You cannot feel it. It does not threaten you. It is simply there, doing its work, shaping orbits, bending light, keeping its silent watch, and this journey in your mind. As you drift towards sleep, remember just this: a black hole is not a monster waiting in the dark. It is a natural outcome of gravity, of stars living and dying, of matter obeying the same laws everywhere. It is a region where time slows, where light is trapped, and where our best theories are tested. It is a mystery we are slowly, patiently learning to understand. In the darkness of a black hole, there is not chaos, but a deep, orderly curve in the fabric of reality. And around that darkness, the universe shines, with stars, with galaxies, with the light of countless suns. You are made of the same atoms those stars once forged. You are part of the same universe that contains black holes, nebulae, planets, and life. You are not separate from this cosmic story. You are inside it. Rest now with that thought. The stars have their paths. The galaxies have their dance. The black holes have their silent, watchful gravity. And you have this moment of quiet at the edge of sleep, floating peacefully among them all. Somewhere far away, two black holes circle each other for the final time. They spiral closer and closer, slowly losing energy to ripples in space-time. At last, they merge, becoming one. A brief ring of distortion vibrates, then fades. The new black hole is calm, a little more massive than before. The waves from their joining spread across the universe, stretching and squeezing space, whispering of their existence to anyone who knows how to listen. By the time those ripples arrive here, they are incredibly faint. Most of the earth does not notice. Life continues, unaware. But a few quiet instruments in silent tunnels feel the slightest shiver. From that, we reconstruct a story of mass, of distance, of ancient collisions. We turn that story into understanding, knowledge, and perhaps, tonight, into a soft, slow tale to fall asleep to. In the timeless dark between the stars, black holes wait, not as villains, but as markers, as boundaries where our understanding is still growing, as reminders that nature can be stranger than our first ideas, yet still follow simple rules. Gravity pulls, space curves, time flows, light travels, and where gravity grows too strong, a horizon forms. On one side, the universe we know. On the other, a region we are still learning to describe. You do not need to solve the equations. You only need to rest, knowing that the universe is old, vast, and patient. It has made room for black holes and for sleeping minds on a small planet, thinking about them. Let those thoughts drift away now. The black holes will keep circling their galaxies. The stars will keep burning. The universe will keep unfolding its quiet, grand story. And you can let yourself gently sink into sleep, carried by the simple knowledge that in all this immense and mysterious cosmos, there is also a place for calm, for rest, and for dreams.